Okay, we are going to solve now this problem 1.9 of Griffiths' book, third edition on quantum mechanics. It's a very, very important problem because you'll see again the Gaussian distribution showing up. In this problem, we have a particle, a certain mass m, and the wave function of this associated with this particle, with the motion of this particle, is this one. This a, again, is a constant which could be complex. Then we have this little a here, which is a positive real. Then we have the mass, x squared and h bar plus it. So you see, they are now giving us the wave function in time. Now, the problem that we solved before was a time zero. Now we have a general time, so you see time showing up in this equation. In principle, this big A could be complex. They are telling in the problem that this is also real. Both are real, big A and little a. So question A of the problem is find A. Find A for what? Find A that will guarantee that this wave function is normalized. So what is the procedure? We have to guarantee that this is equal to 1. Okay, so that's the way to go. Since the big A is already real, as they said, I'm going to put A squared outside, but the correct way is absolute value. In principle, it could be complex. The problem told us that it is real, so that's why I'm just putting the square like that. And then inside the integral, we have, well, what is psi, absolute value square of psi? Is the complex conjugate and the function. The complex conjugate, wherever we have I, this becomes minus. So this will be A, in principle could be a complex, minus AM x squared over h bar. And now that I there, this I here will become minus I, but because there is a minus as well here, this becomes plus AIT. So all this is the complex conjugate. Now for the other one, the function itself, I have A, that exponential, oops, there is a little a there, A mx squared over h bar, and the original one, I with minus A minus IET. Okay, so this is the wave function. When we multiply these two things, we get to the absolute value of big A squared. This exponential with this exponential will give us minus 2am x squared over h bar. Now, this exponential with this exponential, what we are doing there is IET multiplied by minus AIET, which is exponential of 0. What is the exponential of 0 is 1. So when I look at the complex conjugate of this part, this is just 1. Okay, so this is what I'm going to put here in our integral. We have minus exponential minus 2am x squared over h bar, and you see that the exponential with I disappear, and we have so just this integral. Well, what is the solution of this integral? This is a Gaussian function. We already talked about, I even explained, and there is a video explaining how we get to the solution for a Gaussian function. So what is going to be the solution? Let me remind you. So let me write it here, that when we have a Gaussian function between minus infinity to infinity, this is equal to the square root of pi over what we have in front of this x squared. No? So Gaussian function or bell curve, as you're familiar with. So this is what we'll do here. What is going to be the solution? We have this a squared. Now, the solution of that integral will be pi over 2am, everything that is in front of the x squared, over h bar. And this, because it has to be normalized, this has to be equal to 1. conclusion of this story, to ensure normalization, this big A has to be equal to 2am divided by pi h bar, all that to 1/4. Okay, so we found big A, we have normalization. The wave function is normalized. Question B is, what is the potential energy function? What is this V that will lead to this solution that we have, that will lead to this wave function? Okay, well, how are we going to do that? We want to find what is the V in the Schrodinger equation that will give us an answer that wave function. Well, let's rewrite Schrodinger's equation. Let me put this in black. This is Schrodinger's equation, correct? And what we want to know is, what is this V? What is this potential energy function? That's our question. So to find that, since we are given the psi, we are going to solve this derivative, and then obtain the V. Okay, so what is the first derivative in time? Remember, the part that we have in time is just this IT, right? So if we do this derivative in time, we have minus little a I, right? And the rest of the wave function just survives as it is. Okay, now, so this is the first term. Now, the second term involves a second order derivative. So let's do this on the side. The first derivative, what does it give us? The first derivative is, we'll have minus 2, because we have x squared, minus 2am over h bar, and the wave function, because it's an exponential, right? You learned that and how to do derivatives of exponential. The exponential remains, and you do the derivative of what is contained in that exponential. Okay, this is the first derivative, but what is then the second? So, oops, sorry, let's correct here. We have 2 from this x squared here. We have 2, correct? But we cannot forget, you see how it's easy to make a mistake? We cannot forget the little x here of the derivative, okay? So now we go for the second order derivative. And what are we going to get? Well, first I'm going to do the derivative in x here. So this gives us minus 2am h bar of the wave function. And then I'm going to do this derivative of that. So we will get then twice what we had before. And the wave function. Okay, so this whole thing is what we are going to put there on top. So we have minus h bar squared over 2m, and then we have all that term. I'll put what we have in common, minus 2am over h bar. So I just copied this because this appears also in the other term. So psi, this psi here, and now we have minus 2am over h bar x squared psi. Okay, so let's get rid of this part to gain some space. Okay, and what is next? On the other side, we have the V that we are trying to find. All right, so now it's a matter of isolating this V, and we'll get what it is, right? So V multiplied by the wave function gives us, this first term becomes plus h bar a. This second term, let's see what we can cancel here. There is this h bar, this m, this 2, this becomes plus, right? So now we have, and this we are going to pass to the left, so we get a minus sign, minus h bar a. Okay, so that's what survived from this term, negative side, because we pass it to the other side. And inside here we have 1 and then minus 2a m x squared over h bar, all that multiplied by psi. So then we get the V, the potential energy. You see, we can cancel this. And so the potential energy is minus, with minus becomes plus. So 2 a, 2m, 2m a square x square, and you see that this h bar cancels. So this potential energy is very, very important, is the potential energy of an oscillator, of a harmonic oscillator, which we'll be learning a lot in this course. Very important um, um, potential energy in physics and other parts of science as well. Okay, this potential energy is associated with wave functions that are Gaussians. And that's why I said that the Gaussian is so important, because it's associated with the harmonic oscillator. We'll see more about it, but be sure you get familiar with the Gaussian because we'll use it a lot in the future. Okay, what are the next questions of this problem? The next questions are just techniques. No, it's integrals that you have to solve. You have to obtain the expectation value of x, the expectation value of x squared, of p, and of p squared. Nothing is very hard here, provided you remember how to solve integrals involving Gaussian functions. And once you have that, you can then get the uncertainty. Well, you can get the standard deviation for each quantity, right? And then use that to check the uncertainty principle. You will see, if you do everything correct, that this will give you exactly the limit of the uncertainty principle. Okay, this will be 0 because you have the symmetric integral of an odd function. This will also be 0 for the same reason. And these are the two that will give you some results. So try to do it. If you have any question, let me know.